Hello, everyone. My name is Niloy Biswas. I'm a graduate student in the statistics department at Harvard University. Today, I'll be speaking about bounding Wasserstein distance with couplings. This is joint work with Lester Mackey. We will put this paper on archive later on this month, so this is ongoing. First of all, I will talk about couplings and Wasserstein distance. Secondly, I will highlight some stylized examples of our upper bounds to Wasserstein distances based on couplings. And lastly, I'll give some more practical applications of our methods applied to assess the asymptotic bias of approximate Markov chain Monte Carlo. To begin with, I'm going to highlight different ways of sampling from some target distribution, P. So we wish to generate samples from P. For example, P could correspond to a posterior distribution of interest in Bayesian inference. How can we do this? In an ideal world, we'd sample from P perfectly. This is difficult to do in general because P can be very high dimensional and not something we can analytically simplify to say in terms of uniforms. So something else one can do is asymptotically exactly sample from P. Markov chain Monte Carlo is a very popular and successful method which falls into this second category. In this category, we generate samples from a distribution PT sequentially, such that as t goes to infinity, the distributions PT converge to the target distribution of interest P. Also, we can do approximate sampling methods. Here, we do not necessarily target the original distribution of interest P, but we target P tilde, where P tilde we believe to be close to P. Approximate MCMC and variational inference are two examples which fall into this third category. I'm now going to describe approximate MCMC with more detail and compare it to exact MCMC. In the exact MCMC setting, we initialize at some initial distribution P0. So we sample from this distribution P0. For every time step T1 or greater, we have a kernel K1, which we use to go from the previous time step xt minus 1 to the tth time step xt. We choose our kernel K1 to be P invariant. This, under regularity condition, ensures that the distribution of a Markov chain converges weakly to the distribution of interest P. So if we run our Markov chain long enough, its distribution will converge to the original target distribution of interest P. Now, in approximate MCMC, we do something very similar. So we have a similar setup where we sample from an initial distribution Q0. We sample this Markov chain YT according to this kernel K2. And K2 here is Q invariant, such that YT goes to this distribution Q as you run the chain for an infinitely long number of time steps. Here, K2, we design to be chosen to be similar to K1, but computationally much easier to calculate. Now, what's the motivation behind this? So we choose K2 to be similar to K1 with the hope that this target distribution Q is close to this original target distribution of interest P. Secondly, why do we want it to be computationally cheaper? In large data setting, where you may have a large number of data points, or alternatively, you may have a very high number of covariates in high dimensional settings. Working with the exact kernel K1 can be computationally expensive each iteration. Therefore, there are classes of approximate MCMC which are motivated by coming up with approximations to K1, which are computationally cheaper, but in terms of the numerical evaluation, similar to the output from K1. So popular examples which cover approximate MCMC are stochastic gradient MCMC for tall data sets, where tall data set refers to examples where we have a large number of observations. So stochastic gradient Langevin dynamics is one example. We also have others. And there is a recent paper in JASA which review some of the stochastic gradient MCMC methods to date. Secondly, we have the wide data setting. Here we have a smaller number of observations, but a much higher number of covariates. So we're working in the high dimensional setting. And there are approximate MCMC algorithms based on either matrix approximations for the John Rowe, Anirban, Bhattacharya, and the Paulo Orenstein paper, or the Skinny Gibbs paper of Naresetti et al., or the recent Achade and Wang paper, which is not necessarily based on matrix approximations, but Taylor expansions about the likelihood. So given the increasing prevalence of large-scale data sets, approximate MCMC has been an area of research which has received much interest. And what we're going to focus on in this project is answering this question of asymptotic bias of approximate MCMC. So how close is this distribution of the approximate chain Q to the target distribution of the exact chain P? Now, to answer this question, we need a notion of distance, and we're going to focus on Wasserstein distance. The Wasserstein distance between the distributions P and Q can be written as an infimum of this expectation. So we have a cost function C. Here, C can be, suppose, a metric on the Euclidean. So if X and Y are both random variables on some d-dimensional Euclidean space, you could think of C as, for example, the L2 norm between X and Y. Now we have an infimum here where the distribution of X marginally is P, the distribution of Y marginally is Q, but X and Y can depend on each other, so they're not necessarily independent. So this can be described as an infimum over all couplings of P and Q. This distance, as defined, is geometrically faithful in terms of a measure between probability distributions, because it directly takes into account the underlying metric of the metric space we're working with. Secondly, it can directly control absolute difference between moments of P and Q. And there is recent work highlighting why Wasserstein distance might be a more favorable quantity of interest compared to divergence-based measures such as KL divergence or Renyi alpha divergence. So given these favorable properties, Wasserstein distance is a useful quantity to focus on, which will be our interest in this talk. In particular, we will use couplings of Markov chains to estimate upper bounds of Wasserstein distances. So the upper bound of the Wasserstein distance between P and Q. Now, we're going to do this by introducing something we call perturbed couplings. So we have a kernel K bar on the joint space such that marginally along one component, my kernel follows the exact chain. Marginally along the other component, my kernel follows the approximate chain. Now, in applied probability, this setup has been very well studied. There are papers more recently, but even going back before, outside of these three I've mentioned, which study the perturbation theory of Markov chains with this setup in mind. We focus in this project on simulating such couplings instead of only doing analytic theory. And we look at using such couplings and simulating such joint kernels to empirically assess sample quality. In particular, for a fixed joint kernel K-bar, we sample the joint chain xt plus 1, yt plus 1, given the previous states xt and yt. For each of the independent coupled trajectories, so the trajectory I would correspond to xti, yti, we define the following estimator, where we're simply averaging over both the independent trajectories and along each trajectory of the cost between x and y raised to the power of p for p Wasserstein. Then, assuming you have a large enough burn-in S, or that you start your chain marginally as stationarity, this upper bound in this quantity in expectation will give an upper bound of the true Wasserstein distance. This follows directly from the coupling representation of the Wasserstein distance I defined in the previous page, where it's given as an infimum over all couplings. Therefore, any fixed coupling will be an upper bound. Now, to quickly highlight a stylized example illustrating our method, imagine P is a d-dimensional Gaussian with non-zero, non-diagonal entries, and Q is a d-dimensional Gaussian sharing the same mean and sharing the same marginal variances as P, but 0 along the non-zero diagonals of the covariance matrix. So in this case, a simple thing one can do is apply common random numbers or synchronous coupling of two metropolis adjusted Langevin kernels. The first Langevin kernel targeting P, the second Langevin kernel targeting Q. And when I say common random numbers coupling or synchronous coupling, what I mean is you sample the same Gaussian, which you adjust based on your gradients for the two chains to get the proposal. And then you sample the same uniform and you use that to accept and reject at the metropolis correction step of the Mahler kernels. Now, under this setup, we get the following results, which I'll explain. First of all, what I'm showing here, the lowest line, which is the dashed black line, is the true Wasserstein distance squared. The line at the very top, this corresponds to the expectation under the independent coupling. The second horizontal line corresponds to the empirical Wasserstein distance with a finite number of samples. Now, this is a 100-dimensional example I'm basing this plot on. So for the empirical Wasserstein distance to be close to the true Wasserstein distance, we need a large number of samples. And here I'm showing that for a smaller number of samples, the empirical Wasserstein distance can be much larger than the true. Lastly, this line, which starts around 200 and then drops down to around 50, this is our coupling-based upper bound estimate as you increase the length of the trajectory. And you can see in this example, as you get to trajectory length 200 and more, and even earlier, this gives you a tighter upper bound compared to the independent coupling and the empirical Wasserstein distance. An important point to highlight here is that if you increase the trajectory length, our upper bound does not necessarily attain the true Wasserstein distance. In contrast, if you look at empirical Wasserstein distance and you had an infinitely number of independent samples from P, an infinitely number of independent samples from Q, then the empirical Wasserstein distance would indeed converge to the true at a very slow rate. But in higher dimensional examples, the number of samples required can increase exponentially in terms of the dimension when it comes to working with empirical Wasserstein distance. Therefore, in this case, we see that our upper bounds perform better than the empirical Wasserstein distance because we're working in 100 dimensions. And also here, because the number of samples used in our upper bound is equal to the number of samples used for the empirical Wasserstein distance. So in this setting, we're already getting some signs that in reasonably high dimensions, our upper bounds may perform more favorably in some settings compared to empirical Wasserstein distance. Now, we can look at these upper bounds for different dimension in higher cases. Again, we can see that for the same number of sample sizes, the black solid line corresponding to our upper bound is a much tighter upper bound compared to both independent coupling and also the linear program-based upper bound, by which I mean the empirical Wasserstein. So in both cases, linear program legend corresponds to empirical Wasserstein. Okay, so now I'm going to highlight a second example of applying our methods to assess asymptotically bias of unadjusted Langevin versus metropolis adjusted Langevin. Here, both of the two chains are targeting P, given by this d-dimensional Gaussian, but the Euler chain does not necessarily converge to P because we do not correct using the Metropolis-Hastings acceptance rejection step. And we again apply common random numbers or synchronous coupling between metropolis adjusted and unadjusted Langevins. Now, the lowest line on this plot shows the true Wasserstein distance squared. The second lowest line, the black solid line, shows upper bounds based on our coupling-based estimates. The third highest line is the analytic bound of Dumus and Moulins from the Benui paper. And lastly, the highest line, the dotted line, corresponds to the independent coupling. So in this example, we are trying to highlight that even in cases where there has been really careful analytic work done to understand the asymptotic bias of unadjusted Langevin compared to metropolis adjusted Langevin, couplings can give you something which is empirically informative. On the other hand, the analytic bounds of Dumus and Moulins explicitly characterize things like dependence on dimension, which empirical bounds that we produce do not necessarily do. Now, I'm going to go into some more practical examples. We will avoid some of the theoretical results in this paper for this talk, but that's forthcoming in the archive version of the paper. So now looking at Bayesian logistic regression, I'm going to highlight our performance on two data sets. The Pima Indians data set, which has roughly 800 observations in just 8 dimension, and the DS1 life sciences data set, which has 27,000 observations and 10 covariates. So DS1 is a much taller data set. And we apply, again, common random number coupling of Mala kernels for a range of sampling algorithms. So here you can see both the two Wasserstein upper and lower bounds, where the lower bounds are based on existing lower bounds, we know. For the two Wasserstein distance with the L2 norm that we can estimate. I will avoid details about the lower bound for the purpose of this talk, but it will be on the paper. Now, let's focus on the Pima Indians dataset as shown by the dashed error bars. You can see of the different sampling algorithms, as expected, SGLD, where we have 10% subsampling of the full dataset, is worse in terms of asymptotic bias than SGLD with 50% subsampling. And Euler is much better, where we actually do not do any subsampling. We look at the full likelihood. Secondly, you can see that Laplace approximation of these posteriors actually has lower asymptotic bias than things like Euler and SGLD, and also mean field variational Bayes. So this highlights the favorable performance of Laplace approximation in such tall data settings where the posterior is log concave and concentration of the posterior leads to the posterior being roughly Gaussian. Secondly, you can see comparing the DS1 dataset with the PIMA dataset that the DS1 dataset produces lower asymptotic bias for all these different sampling algorithms. This is again, as we expect, because the DS1 life dataset is a taller dataset with much higher number of observations, but similar dimension. The concentration of the posterior occurs much more so with the taller dataset, and therefore the Gaussian approximations, for example, the Laplace approximation, will do better with this extra concentration. Okay, so this is the tall data regime. Again, log concave. Now I'm going to highlight a high dimensional linear regression case. So here I consider a publicly available GWAS dataset where now I have a lower number of observations, but much higher dimension. So here I work with Bayesian linear regression with half t-prize based on recent work using couplings with half t-prize. I recommend seeing my second presentation for some details of this. So here I look at using half t-prize with 2 degrees of freedom. And if you look at the beta here, this corresponds to a global local shrinkage prior, where the Cassi is the global shrinkage parameter and each eta j is the local shrinkage parameter for each beta j. So under this setup, we have an exact MCMC chain, which is a Gibbs sampler, which has n squared p cost. P here should be d, corresponding to dimension. And this cost comes from this weighted matrix product, where you have the eta, the diagonal matrix of the etas, being multiplied by x and x transpose. Now, John Rowe proposed recently an approximate MCMC algorithm, where we replace the etas with a truncated version, which I denote eta tilde, where anything below epsilon component-wise is truncated to be exactly 0, as given here. This reduces the computation cost of the matrix weighted product and speeds up the computation cost per iteration. Now, a natural question here is, as you increase epsilon, the approximate MCMC becomes less accurate, less close to the exact chain. And when epsilon is 0, approximate MCMC is the same as the exact chain. But for practitioners, how does one choose this epsilon? And if we want to, for example, control the asymptotic bias of this approximate MCMC chain, can we find ways to choose this epsilon? And we can look at doing common random numbers coupling of this exact chain and approximate chain marginally to get some answer towards this. So here I'm showing 2 Wasserstein upper and lower bounds for this half t prize with 2 degrees of freedom. And I show the approximate MCMC threshold, epsilon, on the x-axis. You can see as I increase epsilon, the Wasserstein distance, upper and lower bounds, are higher. So this gives a nice way to characterize what the asymptotic bias of such chain would be, of such approximate MCMC chain would be, as you increase epsilon, and may help practitioners or even researchers who are developing new approximate MCMC methods. This is very much an ongoing project. We will have something on archive later this month. Thank you.